Page 107. We have several different theorems today to help us take derivatives. The first is called the constant rule. The derivative of a constant function is 0. That is, if c is a real number, then the derivative of c equals 0. For instance, if f of x equals 7, f prime of x equals 0. Now, why is it true that the derivative of a constant equals 0? Because a constant function, if you graph it, is a horizontal line. And what's the slope of a horizontal line? 0. Since the slope of a horizontal line equals 0, the derivative of a constant equals 0. Because what is derivative? Slope. So if y equals 2/3, what does y prime equal? 0. If f of x equals negative 3/4, what does f prime of x equal? 0. Woo! Let's try another one called the power rule. Power rule looks intimidating. It says if n is a rational number, then the function, and by the way, we'll revise the power rule a couple times during the year, and eventually n can be any real number. Then the function f of x equals x to the n is differentiable, and the derivative of x to the n equals n times x to the n minus 1. For f to be differentiable at x equals 0, n must be a number such that x to the n minus 1 is defined on an interval containing 0. And we don't have to worry about that yet. Okay? So here's how the power rule works. The exponent becomes the coefficient, and the new exponent is the old exponent minus 1. So, right here, if f of x equals x to the 9th, the power rule says that f prime of x equals, and then follow what I said here. The exponent becomes the coefficient. The new exponent is the old exponent minus 1. So the derivative is 9x to the 8th. That's really handy, isn't it? Isn't that a lot better than doing the old f of x plus delta x and having to raise that to the 9th power? Oh, yeah. No. It's not the way it works. The exponent becomes the coefficient, subtract 1 from the exponent. I don't know what you're saying exactly, but you're off track. I think.
I'm saying, like, you take the exponent from a 9 to an 8, put 9 out. If you put an 8 out front of that,
No. No. Well, because what you're doing the same kind of reasoning as this. I've had kids do this. Square root of 16 is 4. Then they'll put a square root of that and call it 2. You were done when you had 4. So it's just a one-step problem. Okay? Now, even things that don't look like the power rule will apply to, you can use the power rule on. Look at this second example. If you've got 1 over x to the 5th as your function, rewrite it as x with an exponent on it. So rewrite it as x to the negative 5, and now the power rule applies. So the exponent of, so when you take the derivative, so f prime of x equals, the exponent of negative 5 is now your coefficient, times x, and then subtract 1 from negative 5. And negative 5 minus 1 is not negative 4. Negative 5 minus 1 is negative 6. And then, as much as we can, we attempt to make our answer look like our problem. Sometimes it's just not worth it. But if we can, We make our answer in the same form as our problem was. Yeah.
Can we do the same thing like we have square roots or whatever, like x to the 1/2?
Yeah, if you had the square root of x, you could change that to x to the 1/2, and now you can use the power rule on it.
1/2 x to the negative 1.
Exactly. In a minute we could. Okay? Now, a special version of the power rule you need to know. The derivative of x equals 1. If f of x equals x, that's the same thing as x to the 1, correct? So f prime of x would be exponent becomes the coefficient, then x, then subtract 1 from your exponent. 1 minus 1 is 0. Now, what is x to the 0? 1. Okay? So the derivative of x is 1. That's a special case of the power rule. If y equals x to the 5th, what does y prime equal? 5x to the 4th. If y equals x to the negative 7, what does y prime equal? You with me? Okay. Now, like I said a second ago, sometimes you have to rewrite your function to fit a form you know how to differentiate. For instance, if we're given this, y equals 1 over x squared, rewrite it as y equals x with an exponent on it. Now that it's x with an exponent on it, you can apply the power rule. The exponent becomes the coefficient. Subtract 1 from the new subtract 1 from the old exponent to get the new exponent. And then, as much as we can, we like to put our answer in the same form that our problem was in. So if it starts as a fraction, we'd like to end it as a fraction whenever we can. So rewriting is the first step, well, lots and lots and lots of times. Eventually, it'll almost always be the first step. Okay? So, many times, most of the time, you're going to have to rewrite your function so that you can fit one of your differentiation theorems. Okay? So, don't be afraid to rewrite things. All right, the next one. Next theorem is called the constant multiple rule. If f is a differentiable function and c is a real number, c is a constant, then c times f, so a constant times a differentiable function, is also differentiable. And the way it works is the derivative of that constant times that differentiable function is the constant times the derivative of the function. I know. Look at the way I wrote it. The derivative of a constant times a function equals the constant times the derivative of the function. It's as if we factored out a constant. Think about what the definition of derivative is. It's a limit, right? With limits, weren't we allowed to factor out constants? We didn't very often. It didn't come up very often. But we could. We could factor out, if we had a constant of 8 times whatever, we could factor the 8 out, we put it in front of the limit sign, and then we did the limit, and then at the end we did 8 times that. Same thing. Since a derivative is a limit, the rules that apply to limits apply to derivatives. We can factor constants out, take the derivative of what's left, and then at the end multiply the constant back in there. Okay? Here's how this works. If we have y equals 7x to the 3rd, think of that as a constant multiple rule problem. Think of that as 7 times x cubed. 7x cubed means 7 times x cubed. So think of that when you find the derivative, think of that as 7 times, and then take the derivative of x cubed, which we know how to do with the power rule. The derivative of x cubed is 3x squared. 7 times. So then multiply your 7 back in there. 7 times 3 is 21 x squared.
Why does the power rule work?
Why does the power rule work? Save that, because that you have to see the proof of it. Okay? Now, question you asked a minute ago. What if that numerator had been a 2? Okay? Heck, look, we'll have a numerator of 2 and a denominator of 7. All right, as that's written, we can't find the derivative of that. Okay? Don't assume, oh, it'll be the derivative of the top over the derivative of the bottom. Not only can you not assume that, that's flat out wrong. It doesn't work that way. So instead, rewrite this so we can use the constant multiple rule. 2/7 times x to the 5th. Now that we know the constant multiple rule, we know that the derivative of this will be the constant times whatever the derivative of x to the 5th is. And the derivative of x to the 5th is 5x to the 4th. And then do your best to make your answer look like your problem. So make that 10x to the 4th over 7. Yes? No? Maybe? Lots of yeses. Good. All right, so then look at these examples from the book. Let's see. Example 5 is on page 110. If your function equals 2 over x, rewrite your 2 over x to be 2x to the negative 1, which is 2 times whatever the derivative of x to the negative 1 is. So that's 2. What's the derivative of x to the negative 1? Turn the negative 1 into your coefficient. Subtract 1 from the exponent. And then simplify it all out. 2 times negative 1 is negative 2x to the negative 2, or 2 over x squared. Now, instead of me reading every one of these to you, you read them, either from page 110 or from right here. And look at all the cool things you can do. Rewriting is huge. And I'll even highlight the rewriting step for you. Now, one thing I'm going to do, and I'm going to have you do as well, is let's avoid writing derivative a million times. Rewrite your function to the form you want it to be in, then take the derivative. Okay? As opposed to writing this. Let's not do that. We rewrite our function to get it into the form we want it, then we take the derivative. Okay? You hanging in there? Questions? C. All right. So change the square root of x to x to the 1/2. So you've got your constant out front, 1/2, x to the negative 1/2. That's applying the power rule. You with me on that? All right. 2 times 1/2 is now a 1. So if I've got 1, x to the negative 1/2, make that 1 over x to the positive 1/2. And the x to the positive 1/2, change that to a square root of x. Now, why did we change it back to that? Because we started with a radical. We'd like to end with a radical. Okay, other questions? Oh, we'll get to that. Yeah, and, oh, no, not yet, sorry. We're still 5 minutes away. Okay? We good on these? Oops. These? All right. Now, when you use the constant multiple rule, then the power rule, we call that the combination rule. Okay? The combination rule says this. When you have a constant times x with an exponent on it, instead of doing it as two separate steps, the constant multiple rule first and then the power rule, we can combine them into the combination rule, which says this. Exponent times coefficient, subtract 1 from the old exponent. So for instance, if f of x equals 8x to the fourth, the combination rule, which is the constant multiple rule and the power rule, says multiply your exponent times your coefficient. 4 times 8 is 32. X, subtract 1 from the old exponent, cubed. And we can do it in one step. So the combination rule is the combination of what? The constant multiple rule and the power rule. But you can't do this one. What do you get? Okay. You with me? So what's the derivative of a constant? 0. The derivative of a constant is 0. What's the derivative of x? 1. What's the derivative of x cubed? X cubed, 3x squared. Right? X cubed is x, looks like this. What's the derivative of that? Okay. See, y'all scared me there. All right. Sum and difference rules. If you have two or more differentiable functions added together, the derivative of that is simply the derivative of each little part. Okay? And keep the sign. Now that sounds worse than, especially if you read it. The sum or difference of two differentiable functions, f and g, is itself differentiable. Moreover, the derivative of f plus g or f minus g is the sum or difference of the derivatives of f and g. Think of it as terms. All right? We now, using the power rule, especially the combination rule, we can take the derivative of terms of a polynomial function, can't we? So just take the derivative of each term and then keep either the plus or the minus sign that's between those terms. So for instance, if we have y equals x cubed plus x to the fourth, the derivative of that, dy dx, or y prime, however you want to call it, will be the derivative of x cubed, which is 3x squared, plus the derivative of x to the fourth, which is 4x cubed. If we have this one, h of x equals 2x squared minus 3x cubed, h prime of x will be the derivative of the first term. Use the combination rule, and the derivative of 2x squared is 4x. Keep the minus sign, then the derivative of the second term. Again, use the combination rule, and the derivative of 3x cubed is 9x squared. So we can now take the derivative of any polynomial function, can't we? All right? Because you use the combination rule and the sum and difference rules, and you can take the derivative of any polynomial function. You can take the derivative of a lot of other stuff too. All right? If those terms had square roots in them that we could turn into exponents, we could take those derivatives, couldn't we? Okay? What we can't do, we can't take the derivative of things that are multiplied together unless it's a constant times it. And we can't take the derivative of things that are divided unless it involves just a constant. But we can't do a polynomial times a polynomial unless one of the polynomials is a constant. We can't find the derivative of a polynomial divided by a polynomial unless one of those is a constant. We can't yet. Okay? Sine and cosine. This is cool. The derivative of the sine of x is the cosine of x. But the derivative of the cosine of x is not the sine of x. It's negative the sine of x. The derivative of the sine of x equals cosine of x. The derivative of the cosine of x equals negative sine of x. So if f of x equals x cubed plus the sine of x, f prime of x will equal, what's the derivative of x cubed? This is about the third or fourth time we've had it. Not 2x squared, 3x squared, and now we know that the derivative of the sine of x is the cosine of x. Now look, that's a simple problem, and in a month, you'll be begging for those. Okay? But look, it required several rules. It required the power rule to do the derivative of x cubed. It required the derivative of the sine function to do the derivative of the sine. And it required the sum and difference rule to know that all I had to do is take the derivative of the first term, keep my plus sign, take the derivative of the second term. So that involved 3 different theorems. So, I mean, it's still fairly complicated math, even if the way the problems work out now are quite a bit simpler than they would have been yesterday. It's still, you know, somebody did a lot of thinking to come up with these theorems, didn't they? So, you know, when you say your prayers tonight, you might want to give a little thanks for Newton and Leibniz and the boys. And they were mostly boys. There were some women, but they were mostly boys. The thing is, back in those days, even if the girls figured it out, you know who took credit? Yeah, the boys. I don't know if it was their husbands or not, but the man they were working with pretty much took credit for whatever the women did. Sorry. I wasn't there. Don't blame me. Bet you can't do that one. No. I'll rephrase that. Do that one. All right, everybody get negative 1/3 sine of x? All right, so we rewrote the cosine of x over 3 as 1/3 cosine x. That way, the constant multiple rule applies. All right, so y prime equals 1/3 times whatever the derivative of the cosine of x is. So we've used the constant multiple rule. Now we use the derivative of cosine rule to know that's negative sine of x. Then we simplify it and get negative 1/3 times the sine of x. All right, take a look at these. And see if they make sense to you. A, B, and C all make sense? All right, on C, we're doing the sum or difference rule. So the derivative of x is 1, and then the derivative of cosine is negative sine. Now, there was an intermediate step there where they had 1 plus negative sine, but, you know, plus minus. No. Now, something that we'll have to talk about quite a bit as we go through the years, how much to simplify your answer. For now, Try not to leave negative exponents, and try to make your answer look like your problem. If there's a radical in it, try to answer with a radical. If it's a fraction when you start, try to answer as a fraction. Okay? And try not to leave negative exponents. And as we go through the year, we'll have to revise this from time to time as we get more and more complicated things. Okay? Questions? All right, let's do some of your assignment then. Let's start with number 10. On page 115, number 10, the directions just say find the derivative of the function. Number 10 is g of x equals the fourth root of x. All right, we don't have a rule for this. And by the way, we call them rules. They're actually theorems. People had to figure them out. They had to prove them. Okay? But we don't have a rule for that. But we do if we turn that into an exponent. So the fourth root of x can be rewritten as x to the 1/4. Now you can use the power rule. So if g of x equals x to the 1/4, g prime of x equals, so exponent becomes coefficient, then x, then subtract 1 from your exponent. So 1/4 minus 1 is negative 3/4. All right, then we try to simplify our answer. Let's see, I'd rather not have negative exponents, so I can make that 1 over 4x to the 3/4. And I did start with the radical, but here's where I kind of want to break my own rule. The fourth root of x cubed doesn't really seem any simpler to me than x to the 3/4. So I'll take this. I will also take 1 over 4 times the fourth root of x cubed. Not now. If we run into a situation where one way is beneficial for some reason, you're going to do something with your answer or whatever, then we'll talk about it. For now, I'll try to be flexible and you try to be flexible and recognize either thing as the correct answer. All right, we good with 10?
Yeah.
Let's see, I guess that's the only one on that slide. Let's try 20. All right, so g of t equals pi times the cosine of t. All right, we can use the constant multiple rule, can't we? Because pi is a constant. And then we know how to find the cosine of x. Well, the cosine of t is going to be the same thing, just with a t. So g prime of t equals constant multiple rule, pi, times whatever the derivative of the cosine of t equals. Well, if the derivative of the cosine of x is negative sine of x, the derivative of the cosine of t is negative sine of t. And there's not a whole lot to do to simplify your answer. So negative pi times the sine of t gives us our answer. I like that too. We good with 20? 28. Now in 28, the directions have changed a little bit. They tell us to complete the table. Well, I don't like the table. I don't like going horizontally across my paper. Okay? And you know, most of us do better if we're going vertically down the paper. It's just a little easier to keep your work in order. So instead of filling in the table, I'm going to do the same steps. I'm just going to go vertically down my paper. So the first step in the table is to rewrite the function. We need to rewrite this into a form that we can apply one of the rules to. Well, one of the rules, some combination of our rules. Okay? So into a form that we know how to find the derivative. So first I'm going to do is I'm going to square that 3x. When I square 3x, what do I get? So that becomes pi over 9x squared. But I still don't know how to find the derivative of that because I don't know what to do with that x squared being a denominator instead of just a regular term. So that x squared in the denominator won't work. What do I need to do? Rewrite the x squared as what? Yeah, take it out of the denominator and make it an x to the negative 2. So leave your pi over 9 and then take that x squared out of your denominator and make it an x to the negative 2. Can I find the derivative now? Yeah, it's the combination rule, isn't it? I have a constant times x to the n. So the answer will be x, well, y prime equals, or dy dx equals exponent times coefficient, so negative 2 times pi over 9, x, and then subtract 1 from the original exponent. Negative 2 minus 1 is negative 3. And then let's simplify our answer. So negative, and then I don't want to leave that negative exponent. So I'm going to have the negative out in front. I don't want a negative exponent, so I need a denominator. So what stays in the numerator?
2 pi.
Yeah, negative, and then the 2 pi. And what goes in the denominator? 9x to the third. No, they're not terrible at all. $36. This time the directions say to find the slope of the graph of the function at the given point. Use the derivative feature of a graphing utility to confirm your results. So the slope of the graph is the same. That terminology means the same thing as the slope of the tangent line. Okay? So we've got to find the slope of the tangent line at the point 5, 0. Now, even though we now have some theorems to help us with finding our derivatives, the derivative is still the slope, isn't it? It's just that we don't have to use the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. We could, but I don't suggest it. I suggest using these theorems. Okay? So for 36, we have f of x equals 3 times the quantity, 5 minus x. That quantity is squared. We will have a method to find this derivative as it's written, but we don't yet. So what do we need to do? What methods can we use? We can use the power rule, we can use the combination rule, we can use the sum or difference rule. This one doesn't have sine or cosine, that doesn't come into play. So I need to get this written with as a bunch of terms then, don't I? Terms we're good with. Polynomials we're good with. Now that is a polynomial function. It's just not written as one term plus another term plus another term. We need to get it in that form. So,
Coach Duncan, come to the office, please. Coach Duncan.
first, square the binomial. A minus b, quantity squared, turns into a squared minus 2ab plus b squared. So that's 5 squared minus 2 times 5 times x plus x squared. And we've got the 3 in front. Now, distribute the 3. So look, I've done no calculus. That's still f of x. That's not f prime of x. That's f of x. I've rewritten f of x into a form where I can now use, well, in fact, I can take the derivative of a constant, then I can use the combination rule on the negative, or the constant multiple rule, really, on the negative 30x, and then the combination rule on the 3x squared. And the reason I'm doing it one term at a time is the sum or difference rule. Constant multiple rule, or the combination rule, really. Works out the same either way. So here we go. F prime of x equals the derivative of 75 is 0. The derivative of a constant is 0. Then the derivative of negative 30x. Think of this as the constant multiple rule. It's negative 30 times whatever the derivative of x is. And the derivative of x is 1. That was a special case of the power rule. So that's negative 30 times 1. And then use the combination rule to get the derivative of 3x squared. 6x, and 2 minus 1 is 1 for the new exponent. And we used the sum or difference rule to know that we just added those two results together. With me? So we found the derivative. And that's a good version of the derivative, isn't it? That's fine. I mean, I guess maybe I'd rather have it written as 6x minus 30, but, right? Okay, what are we supposed to do with this? Find the slope at the point 5, 0. So at 5, 0, f prime of 5 equals, well, then you put in a 5 for x. So negative 30 plus 6 times 5. Yeah, negative 30 plus 30 is 0. So we know now that the slope of the graph at the point 5, 0 is 0. In other words, we now know that the slope of the tangent line at the point 5, 0 is 0. What kind of tangent line is that if the slope of it is 0? It's horizontal. We have a horizontal tangent line at that point. It does. Like that. Oops, I missed. Think of it this way. Let definitions handle it for you. The slope of the graph is defined to be the slope of the tangent line at a given point. So if we say the slope of the tangent line is 0, or we say the slope of the graph is 0, they mean the same thing. So if we graph a linear function, since the slope of the graph is, I don't know, we'll make it up, 2/3, since we've defined the slope of the graph to be the slope, to equal the slope of the tangent line, we can now say the slope of the tangent line is also 2/3. Which in this weird, this can only happen in math way, means that a line is its own tangent line. And that just creeps me out too. Is that what's creeping you out? Yeah. So we handle it through definitions. The slope of the graph is defined to equal the slope of the tangent line, and then that kind of takes care of our little paradox there. Okay? All right, we good with 36? 46. Told you we were going to do 52 of them today. Find the derivative of the function. All right, so y equals 3x times the quantity 6x minus 5x squared. We will eventually have something called the product rule, where we could find the derivative of two different functions multiplied together. Even once we learn the product rule, the easiest way to work this one is just going to be multiply the 3x through there, distribute the 3x. When you're in 4th semester calculus in college, this will still be the easiest way to work this problem. Okay? Now that we've done that, we can use our sum or difference rule with our combination rule to get the derivative of y. So, y prime equals, what's the derivative of 18x squared? Yeah, according to the combination rule, it's exponent times coefficient. 2 times 18 is 36. X, and then subtract 1 from the old exponent. So, x. X to the 1, x. Copy down the minus. And according to the combination rule, what's the derivative of 15x cubed? 45x squared. Exponent times coefficient, 3 times 15 is 45. Then your x, then subtract 1 from the old exponent. 3 minus 1 is 2. At this point, you don't have to. We will learn shortly that to use the derivative to do something else, quite often we will need to factor. So if you want to factor your result, you can, but you don't have to yet. Mm-hmm. Whoa, what did I do? Okay, make that go away. There you go. All right. Questions? Page 115.
Make it bigger.
It's just 1 through 52.